Hello again. This is Taylor from Singapore Green New Deal. This is the second video of the three-part series, and in this video, I'm going to respond to your questions about engineering solutions for reducing greenhouse gas emissions, decarbonizing for Singapore. The first question: what are the renewable energy sources Singapore can make use of? For a complete review of all the options for reducing greenhouse gas emissions for Singapore, do read the full report that I published titled Decarbonizing Energy in Singapore, and also the Long-Term Low Emissions Development Strategy report, which was put together by the Singapore government agency, the National Climate Change Secretariat. If you haven't had a chance already to read the report yet, don't worry. I'll summarize the important highlights here in this video. Remember that the problem of climate change is to reduce emissions of greenhouse gases. Currently, we burn fossil fuels and release the CO2 directly into the atmosphere, and that's what's causing the problem. There are 7 basic, scalable alternative energy sources, which have a substantial improvement in greenhouse gas per kilowatt hour. That's solar, carbon capture and storage, or CCS, nuclear, wind, hydroelectric, biomass, and geothermal. Beyond these 7, there are others like tidal, but they're only available on a small, limited scale. Keep in mind that there's a difference between renewable and low carbon. For climate change, strictly speaking, it's only required to switch low carbon energy sources. For example, while nuclear energy is non-renewable, it is also one of the lowest for greenhouse gas emissions per kilowatt hour of energy produced. It's probably critical for reducing emissions in line with Paris Agreement goal of 1.5 Celsius. Motivation for renewable versus non-renewable is an additional requirement on top of the goal of reducing greenhouse gas emissions for climate change. Of these 7, within Singapore, only the first 3, solar, CCS, and nuclear, are available within Singapore's territorial borders. Beyond Singapore's borders, it's possible for us to import wind, solar, and others like hydroelectric and geothermal. We can do this by importing from our neighbors by electrical cable, and that's what we refer to when we're talking about the ASEAN power grid. That's 2 steps though. First, you need to finance the new energy investments in the region, and then you need to arrange for importing into Singapore. Now keep in mind there are also 3 technical challenges to renewable energies. The first one has to do with the intermittency, which means that it's not available when you need it. So when it comes from the sun or the wind, it comes when the sun shines and when the wind blows. That may not match when you need it. The second problem is a problem of thermal energy sources. The third problem is a problem for transportations and the fact that some of these options are not substitutable for certain transportation modes. First problem, for solar and wind, they are intermittent source. For an explanation video about this problem, you can check out the Volks video on YouTube under the search term the duck curve. And here is an illustration of exactly what that duck curve is. You see, the sun doesn't shine at night. It only shines in the daytime. But the energy demand, which is the top curve here, is not exactly the same. So you get these extreme conditions where during the daytime you have more energy than you need, and in the nighttime you have less energy than you need. So that creates a problem, a time inconsistency problem. In order for these systems to be utilized at scale for a citywide energy system, there would need to be a lot of big batteries to store this energy between when it's generated and when it's consumed. Building all of those batteries would consume material resources, minerals, that would need to be mined and extracted from the environment. When there's a mix of renewables with either nuclear, CCS, or hydroelectric, it's less of a problem because with these other sources are dispatchable, which means they can be ramped up and down with changes in demand and availability of renewables. Conservatively, Singapore could safely put up to 50% of renewable energy in the grid, but it would need to be supplemented with some other 50% from dispatchable sources, such as CCS, nuclear, or some import or storage solution. The second issue has to do with the thermal energy demand. Renewables cannot on their own directly supply thermal energy for conversion process. We use thermal energy in industrial processes like steel manufacturing and basic chemical production. such as the furnaces that you see here in this photo of these burners, like the ones that I worked with previously in my job on Jurong Island. In order to make hydrogen from a renewable source, there needs to be an intermediate step that converts the electrical energy into a thermal source. But that conversion process comes with an energy loss that's quite high now. Only about 10% of the energy is converted. That's pretty low. Now, it could get better, but for now, it's more at a research and development stage or prototype stage, and it's not competitive with the other alternatives that are listed here, such as using steam methane reformer with CCS, or by using nuclear to generate hydrogen. When you convert renewables directly into hydrogen, it's known as green hydrogen. The third problem is a similar problem that's related to the storage and the thermal issue, is that there's no real substitute for certain types of transportation modes like shipping and aviation. While we can shift to electric vehicles for road transportation, that also comes with material and environmental resource costs for all those batteries, and there aren't any immediately deployable alternatives for aviation and shipping. This is a problem not only for renewables, but for all the low-carbon alternatives. So we need to move away from these modes of transportation altogether to rail or nuclear-powered ships. For aviation, it's best to do as little of it as possible since there are no climate-friendly solutions. I've mentioned carbon capture a few times already, and by now you may be wondering what that means. Carbon capture and storage is not anything new or experimental, but is a mix of existing technologies that's been around for decades, which means that it can be immediately deployed and can be scaled up quite rapidly. The process is easy enough to understand. You use the same process for natural gas and other fossil fuels. You capture the carbon dioxide that comes out of the stack, and then you put it back in the ground, where it can be geologically stored for 100 to 1,000 years. While it's true that it's not a permanent long-term solution, that certainly buys you a lot of time. According to the IPCC and other scientific reports on emission pathways, regionally CCS is required to meet the Paris Agreement and make progress on sustainable development and reducing poverty. It's dispatchable, meaning that the load can be adjusted to meet fluctuation demand, unlike the intermittent sources we just mentioned, and it's available 24/7. In terms of life cycle environmental footprint, next to nuclear, it's one of the lowest in terms of land use, mining inputs, and residual carbon emissions. It's very land efficient, which is ideal for a land limited place like Singapore. Finally, it's the only solution that's available currently right now at competitive costs for industrial sources of emissions, the thermal energy sources I mentioned for cement, steel, and some manufacturing processes that require high temperature conversion. So what's the catch? Well, the drawback of carbon capture is the cost. So it doesn't pay for itself because it's a disposal cost. Fortunately, these costs can be covered with carbon pricing in line with the social cost of carbon as determined by the IMF and other international institutions and economists, although with the right design of carbon tax policy, low and middle income families don't need to be bearing the burden of these extra costs and taxes because there are just transition, Green New Deal, and revenue neutral carbon pricing. So there are a lot of ways of making sure that this doesn't reach everyday people. But either way, it's just a matter that environmental compliance has a cost, and it's worth paying. So in summary, for all of these solutions listed that have been identified, um, with a, there's when we get into what Singapore is doing about it, um, let's get into a status update. So the first thing is the Singapore government has yet to come forward with a plan for how to reduce emissions from the oil and gas or petrochemicals industry that would be in line with the scientific targets. Currently, they don't really have a plan. That represents one of the largest single sources within three companies of 45% of emissions. The second issue is that the domestic solar plans that Singapore currently has are not quite ambitious enough. It's far from what's required in order to reach net zero by 2050. We would need to, what they currently have planned is maybe 20 kilometers squared versus maybe 150 in order to meet that 50% requirement that I mentioned earlier. So significant scale up or paradigm shift on domestic solar would be required. The other gap in terms of what Singapore is currently doing is that while CCS has been listed as an option, there's no real plan to deploy it at the moment, and the reason is because there's no money to fund it. And the other status on the three areas that could be implemented for Singapore is nuclear. And the status on nuclear is that there was a research paper that was published in 2010 which had identified siting locations and what would be required. However, there's little information available on subsequent and most recent status is that in a feedback from the public, the Singapore government responded that they have done a pre-feasibility study. However, they have not shared this information with the public. Currently in China, Japan, and Korea, France, and Scandinavian countries, and the US, they all have nuclear included in their greenhouse gas reduction plans. It's also included in the IPCC report. The next question. Can we implement more solar panels in Singapore? I want to use more clean energy without worrying about the negative effects. Why can't we install more solar panels like all over the buildings, or on the walls, and everything so that we can maximize use? All right, so you can read in detail about Singapore government's plans for domestic solar deployment in the Solar PV Roadmap by Ceres Research Institute. And additional analysis for options not considered by the Ceres report is included in the Decarbonizing Energy report. For the question, there are 2 points to consider. Land use paradigm shift and the difference between utility scale and rooftop installations. The area in kilometers square identified in the Ceres report for deployment is fairly limited, a maximum of 50 kilometers squared, compared to Singapore's total land mass of 740 kilometers squared. The report mentions that to move to greater deployment would demand a paradigm shift in the Urban Development Authority, URA, approach to land zoning. There are ample large parcels of land available on the island for utility-scale solar that are currently being used for other purposes, such as military, which is about 144 kilometers square on its own, or golf courses. As you can see here, I have identified just a few examples by just looking at a map of Singapore of land areas that could potentially be utilized to get up to the full 150 kilometers square. Some examples here is the Southern Islands, which is 9 kilometers square. Tekong, which is currently reserved for military use, 48 kilometers square. Ubin, Silitar, which includes a few golf courses. So, and there's an area over by Changi Airport, which is currently not developed at all. It's a big patch of land that could easily be used for solar. So there's no lack of land. To be clear, it's a matter of choice. The land is there. While solar PV is renewable and lower cost than other energy sources, there are limits. The most cost-effective deployment is utility scale, where you have a big flat area that's unobstructed by buildings. When you get into deploying on rooftops, there's an added cost of getting onto the rooftop, blocking from nearby buildings. So when you add in these costs, it starts to appear less attractive. So while the Ceres report identified rooftop areas on HDBs, this is less ideal compared to wide open spaces. The report put in a lot of conservatism in its estimate for what's considered available. For example, it did not include much of building integrated PV, BIPV, because it made a conservative assumption that citizens would complain for aesthetic reasons, meaning, they would complain that it doesn't look pretty to look at a building that's covered in solar panels. So this is something that can change through citizen activism if youth can convince parents that they don't mind the aesthetics. So this is possibly an area where there's room for citizens' voices to open up more options. Still, though, there are the hard engineering and cost limits to contend with, and it would probably be much more feasible to look at the utility scale options first. The next question, how long will it take for solar panels to be more affordable to less developed countries? Well, affordable is not a hard and fast concept, but a relative and subjective. All of the low carbon options are worth the investment. While I can tell you how much each of these cost in dollars per CO2 equivalent or dollars per kilowatt hour, it's up to you whether you think affordable to absorb the cost of climate change, which is what we are comparing these costs against. Some of these options are already cheaper than fossil fuels, not including CCS. The social cost of climate change is around $40 to $60 per ton of equivalent of CO2, so keep that in mind when we're talking about what affordable is. Most economists recommend you not look at it that way and instead assume that we must implement them and just look at which one of them is the cheapest. You can see a comparison of each of these costs in the technology report. Utility scale solar is already now cheaper than natural gas without CCS. Keep that in mind. One way to look at decarbonizing is to look at something that's known as the cost abatement curve. What this is on the x-axis, you have the amount of emissions that we need to reduce globally. And then on the y-axis, you have the cost in terms of dollars per ton of CO2 avoided. Now you notice that on the left-hand side that these are negative. That means that it pays for itself. That means potentially you can finance it through the corporations or the banks. But when it starts to get towards zero, and even when it goes above zero, that means that it doesn't have its own payback. It means it's a pure cost, which means that cost just needs to come from somewhere. And most likely that would be governments, the public, because this is a public problem. No private company is going to be able to pay for anything that's on the right-hand side of this curve. That's not how they work. Economists have recommended to policymakers to budget for around 1 to 2% of GDP, or Singapore $100 per ton of CO2 emissions, or per ton of CO2 carbon dioxide avoided. The current carbon tax in Singapore is too low to be able to do what is needed on the right-hand side of the curve. It's currently Singapore $5 a ton, with a plan to increase only to Singapore $15 per ton by 2030. As you can see, that won't finance hardly any of these options on the right-hand side of the curve here. So it's too low. Another question. A random thought, but can chlorophyll in plants be used to generate electricity? Considering the fact that it's kind of trapping light, like carbon dioxide traps heat, is it possible for it to be converted into electricity like how solar panels work? Won't it be cheaper and more accessible options compared to solar panel? Okay, so this is known as biomass, and surprisingly, it's not as attractive in terms of total life cycle environmental impact, dollars per CO2 avoided or dollars per kilowatt hour. You may be surprised to learn that very little of the sunlight that actually reaches a leaf is actually put into use by the plant. Most of it is rejected as waste heat for evapotranspiration and is not actually converted into biomass. I listed it and compared it side by side in the report, and it's listed at the bottom of these lists for these reasons. It might not be possible to improve, and it may be possible to improve and optimize down the road, but for now it's not an attractive scalable option compared to the others. Question number 5. I know this is weird, but do you think it's possible instead of having roads and traveling by car, Singapore can build rivers and we can travel via boat and ship instead? Not only will it help to reduce carbon emissions from cars because people need to row their own boat, because it would also allow for space and for water to flow and to slow down the amount of land that is being lost. Okay, so a few things. First thing is that cargo shipping is more energy efficient because of its low friction losses for long distances. So is rail for similar reasons. Rail can be electrified, whereas for cargo ships, you would need to have a nuclear-powered ship. So, in my personal opinion, I think it would be a massive undertaking to dig canals, as you described. That would be a lot of money, and I think you'll find that if you add up the cost, it would be cheaper to invest in expanding the public transit system, high-speed rail connectors in ASEAN, reducing car ownership, encouraging shared ride services, and and also the converting the fleets into electric. Singapore is already on track for converting the road transport emissions. So I don't think there's, I think their plan's pretty good. This was a creative suggestion, so keep thinking. It is a weird suggestion, but keep probing and exploring. All right, the next question. In what other ways can global warming be prevented? Well, there are no long-term alternatives other than reducing greenhouse gas emissions. That's the only long-term option. Now, there is the option of geoengineering, which basically means where you force the atmosphere to reflect more incoming light by injecting aerosols. That's not really a very popular option for a few reasons. First is it's quite risky. We could unintentionally either collapse ecosystems from things like eutrophication, or worse, we could overshoot and send the Earth into an ice age, which would have worse consequences possibly than warming the Earth. The other drawback of geoengineering is it's really only delaying the inevitable, because you have to continue to keep supplying the aerosols to block the sunlight, and the moment you stop, whether you run out of money or lose the political will, or could be many reasons, then you're right back to where you started again. It doesn't take greenhouse gases out of the atmosphere. If you continue to emit greenhouse gases in the atmosphere, then you would be worse off, as all the greenhouse gases would still accumulate. They wouldn't go anywhere, and it would lead to warming just as now, once you stopped with this geoengineering program. So it just masks the problem, but it doesn't actually solve it.
Thanks for watching the video. I hope you learned something about options for decarbonizing Singapore. Check out the next video for questions about the international and Singapore policy response to climate change.